Exercise 8.2, question number 15 is summation 0 to infinity 1 over n factorial. We have to check whether this series converges or diverges. For that purpose, if you have this kind of series, that is 1 over n factorial, we know that we have n factorial that will be equals to n into n minus 1 into n minus 2 up to 1. And we also know that if we have n is greater or equals to 1, then this n factorial, that is n into n minus 1 into n minus 2 up to 1, will be greater or equals to, if we just multiply 2 up to n minus 1 times, that is n minus 1 times. And this thing we know that this is n factorial, so this n factorial will be greater or equals to 2 raised to power n minus 1. And this thing holds for if we have n is greater or equals to 1. Now we need here 1 over n factorial, and it is n factorial, so take the reciprocal on both sides and invert them. We will get 1 over n factorial. This sign will also become positive, that is less or equals to 1 over 2 raised to power n minus 1. And we know that summation 1 to infinity 1 over 2 raised to power n minus 1 is a convergent series. So since it is convergent, this is our Bn. Since this Bn is convergent, so it means our An is also convergent. This implies that summation 1 to infinity 1 over n factorial is convergent by comparison test. So summation 0 to infinity, you know that if we add or subtract some terms in a series, it will not alter its convergence or divergence. So summation 0 to infinity 1 over n factorial is also convergent series. Question number 16, that is summation 1 to infinity e raised to power 2n plus e raised to power minus 2n divided by e raised to power n plus e raised to power minus n. Now here our an is this term. An is equals to e raised to power 2n plus e raised to power minus 2n divided by e raised to power n plus e raised to power minus n. Now here we cannot conclude about the term bn. So let bn here is equals to 1, because if we just consider, if we have like function of 1 over 1 plus n raised to power 3, then we take this term as bn. Or if we have n over 1 plus n cube, we take this term as our bn. But here we cannot say our any term regarding to bn, so just let bn is equals to 1. Now we know that summation 1 to infinity bn, that is equals to summation 1 to infinity 1, is always divergent series. This diverges. So let's just observe the behavior for after finding the limit n approaches to infinity an over bn, limit comparison test. If the limit comparison test is not equals to 0, then this behavior will be the same behavior for an. So limit n approaches to infinity an over bn, that is equals to limit n approaches to infinity an is this term, e raised to power 2n plus e raised to power minus 2n divided by e raised to power n plus e raised to power minus n, and divided with 1. And that division with 1 plays no role here, so I'm not writing it here. Just before applying the limit, I am simplifying it. It will become limit n approaches to infinity. I am taking e raised to power n common from the denominator and from the numerator, e raised to power n. We will be left with e raised to power n plus 1 over e raised to power 2n divided by, here we will get, if we just first of all simply you can write it like this, e raised to power, simplify it like this, e raised to power 2n plus this negative term can be written as 1 over e raised to power 2n, and this one can be written as e raised to power n plus 1 over e raised to power n. Now take e raised to power n as common. We will left here limit n approaches to infinity, e raised to power n when taken outside, we will be left with e raised to power n plus 1 over e raised to power 3n divided by e raised to power n common 1 plus 1 over e raised to power 2n. This will be cancelled. So we will be left here with limit n approaches to infinity, an over bn is equals to limit n approaches to infinity e raised to power n plus 1 over e raised to power 3n divided by 1 plus 1 over e raised to power 2n here. After applying the limit, you will observe that this term will goes to 0. So in the denominator we will have 1. But in the numerator we will have this undefined term. And you know that this is not equals to 0. So it means whatever behavior we got for Bn, that will be the same behavior for An. So this shows that the given series diverges because summation 1 to infinity Bn diverges. Now come on question number 17. That is summation 1 to infinity ln n over n. Now an here is ln n over n, and we can take bn is 1 over n here, and we know that ln n, we know very well that ln n over n is less or equals to 1 over n here. Now our bn, observe the behavior of bn. You see that this bn is always 1 over n. This is a harmonic series and it always diverges. Now for using the limit comparison test, limit n approaches to infinity an over bn, that is equals to limit n approaches to infinity an is ln n over n divided by bn is 1 over n. So here we will get limit n approaches to infinity n ln of n over n. This will be cancelled. We'll get here limit n approaches to infinity ln n, and that is undefined. So it means if whatever the behavior we will get for bn, this will be the same behavior for an. And we know that summation 1 to infinity 1 over n is a harmonic series. And it diverges. It diverges. Therefore, summation 1 to infinity ln n over n also diverges. Question number 18, that is summation 1 to infinity 1 plus 1 over n raised to power n. Now an here is 1 plus 1 over n raised to power n. Let bn here is 1 because we cannot take any term out for bn after simplification. So just let bn is equals to 1. Now using the limit comparison test, limit n approaches to infinity an over bn, that will be equals to limit n approaches to infinity 1 plus 1 over n raised to power n. And you know that this is equals to e. And this is not equals to 0. So it means whatever the behavior we'll get for the bn series, that will be the same behavior for an. And we know that summation 1 to infinity 1 diverges. This implies that summation 1 to infinity 1 plus 1 over n raised to power n also diverges. Now an term is sine of pi over n. Take your bn, we can simply take out the n term here, that is bn will be taken as 1 over n here. Now using the limit comparison test, limit n approaches to infinity an over bn, that will be equals to limit n approaches to infinity sine pi over n divided by 1 over n. This will be equals to, you know very well, this will be equals to, we need here the same function here For that purpose, I am multiplying it with pi and dividing it with pi as well. So for that purpose, limit n approaches to infinity, sine pi over n can be written as here pi over n into 1 over pi. And you know that this thing is equals to 1. So pi will be moved up, we'll get pi into 1, that is equals to pi here. This pi is not equals to 0. So whatever the behavior we'll get for bn will also be behavior for an. And we know that summation 1 to infinity bn diverges because it is a harmonic series. So this implies that summation 1 to infinity an also diverges here. Question number 20 is summation 1 to infinity 1 over e raised to power n square. We know that e raised to power n square is greater than e raised to power n. And also, if we just take the reciprocal, 1 over e raised to power n square will be less than 1 over e raised to power n. So we can take this term as our bn. An here is 1 over e raised to power n square. And bn here is 1 over e raised to power n. And we know that summation 1 to infinity 1 over e raised to power n converges. It always converges. So this implies that the series that is summation 1 to infinity 1 over e raised to power n square also converges. By the limit comparison test. Now for question number 21 to 40. Test each series for convergence or divergence. Now they have not specified it like which test you have to use. You can use here any test to check whether it is converging or diverging. So let's start from question number 21. Summation 1 to infinity n square e raised to power minus n cube. I can use here the integral test, and for the integral test, using the integral test, our function must be positive, decreasing and continuous on the interval. Our function must be positive, continuous and decreasing function on the interval. Then we can use the integral test. That is given on your book, page number 343. The integral test, or you can say like Cauchy integral test, let summation 1 to infinity an be a positive term series if f is continuous and non-increasing function. Non-increasing function means you have the decreasing function. On the interval, what the interval is? In this interval, 1 to infinity. If your function is continuous and decreasing function in this interval, then you can say like find out the integration answer, that is integration is from 1 to infinity an. If this integration converges, you are getting the defined answer here, then it means it is convergent. If it is convergent, so this means that your given series is convergent. And if it is divergent, then this means that your given series is divergent. So let's use this integral test here in this question number 21. Our f of x here is x square e raised to power minus x cube. You can write it like f of n as well, but I am using here f of x. Now for checking the increasing or decreasing function, you know that you use the first derivative test. Find out the derivative of this function. Finding the derivative of this function, you will get here 2x e raised to power minus x cube into 1 minus 3x cube here. And that is less than 0 for the interval 1 to infinity. This means that this is a decreasing function. Also, it is continuous and positive. This function is continuous and positive in this interval, and it is decreasing as well. So you can use here the integral test, and that is integration from 1 to infinity x square e raised to power minus x cube dx. This will be equals to limit t approaches to infinity. Now move the integral. You have the limits of integration from 1 to infinity. Now you have converted it into the limit form. So it will be converted into 1 to t here. Limit t approaches to infinity and the limits of integration are converted into from 1 to infinity to 1 to t, the defined integral. And you will have inside x square e raised to power minus x cube dx here. Now you can integrate it well. You know that this function, what is the derivative of this function? Its derivative is minus 3x square. You can make here minus 3x square by just dividing it with and multiplying it with. Now your integration answer will be, you will have here minus 1 over 3 e raised to power minus x cube, and the limits of integration are from 1 to t and limit from t to infinity here. So this will become here minus 1 over 3 limit t approaches to infinity. First of all put the upper limit and then put the lower limit. You will get here 1 over e raised to power t cube minus 1 over e here. Now if you put the limit t approaches to infinity here, e raised to power infinity will be infinity and 1 over infinity will goes to 0. So you will be left with only minus 1 over 3 into minus 1 over e. So your integral answer will be 1 to infinity x square e raised to power minus x cube dx will be equals to 1 over 3e. And this is your defined answer. It is not equals to 0. So it means this is converges. It converges. Since this integral converges, so this means the given series converges. Now I need to take here some bn from here. We know that this 2n minus 1, we know that very well, 2n minus 1 raised to power 1 over 3 will be greater than n raised to power 1 over 3. Because here you see the 2 is multiplied with it and then after subtraction and you have the power 1 over 3 here. So this term will be greater than n raised to power 1 over 3. But we have here in the reciprocal form. So just take the reciprocal, it will become 1 over 2 raised to 2 into n minus 1 raised to power 1 over 3 will be less than 1 over n raised to power 1 over 3. So this term is our bn. An here is 1 over 2n minus 1 raised to power 1 over 3 and bn is 1 over n raised to power 1 over 3. Now use the limit comparison test. Limit n approaches to infinity, an over bn, that will be equals to limit n approaches to infinity 1 over 2n minus 1 raised to power 1 over 3 divided by with this bn, that will become n raised to power 1 over 3 here. So this is basically equals to limit n approaches to infinity n over 2n minus 1 raised to power 1 over 3. Now take n common, it will become limit n approaches to infinity n over n. After taking n common, I will get here 2 minus 1 over n here. And the whole power is 1 over 3. This and n can be cancelled out. So we will get here limit n approaches to infinity 1 over 2 minus 1 over n raised to power 1 over 3. If I apply the limit n approaches to here, this term goes to 0. So I will get here 1 over 2 raised to power 1 over 3 and this is not equals to 0. So observe the behavior of bn now. You know that summation 1 to infinity 1 over n raised to power 1 over 3 diverges. Because you know that I told you earlier the p series. If you have this kind of series, summation 1 over n raised to power p, and your p is less than 0, then it will be divergent. And if your p is greater than 0, then this will be convergent series. And you see here, this p is 1 over 3. This is equals to 0.3 something like that. And it is less than 0. You will have here 1. Sorry, you will have here 1. And you see that this is less than 1. So your series is divergent. Since your bn is divergent, it means that your an is divergent also. Summation 1 to infinity 1 over 2n minus 1 raised to power 1 over 3 diverges. Now move on, question number 23. Consider this term 3n plus 1. This is 3n plus 1. You know that this is greater than 3n. And if I take its reciprocal, 1 over 3 raised to power n plus 1 will be less than 1 over 3 raised to power n. Now I need 2 raised to power n. So multiply 2 raised to power n on both sides. Multiplying anything on both sides will not alter this chain sign. So the behavior will remain same. So you observe that your an is less than bn here. And this one is your bn term. So an is equals to 2 raised to power n over 3 raised to power n plus 1. And bn here is 2 over 3 raised to power n. This one. Now you know that this summation 1 to infinity 2 over 3 raised to power n is a convergent geometric series. So this implies that summation 1 to infinity 2 raised to power n over 3 raised to power n plus 1 is also convergent. Question number 24. Summation 1 to infinity ln n over 1 plus ln of n. Now we can use here the simple divergent test. The simple divergent test is also given on your book in point 8.15. Corollary 8.15 divergence test. If limit n approaches to infinity an is not equals to 0, then this series is divergent series. So I will just find out the limit of this and I will see whether it is equals to 0 or not. Now an here is ln n over 1 plus ln of n. Now limit n approaches to infinity an is equals to limit n approaches to infinity ln n over 1 plus ln of n here. This is equals to, by using the L'Hopital rule, you can see here that limit n approaches to infinity. Use the L'Hopital rule here. Take the derivative of numerator separately and the derivative of denominator separately. Derivative of numerator will give you 1 over n and derivative of denominator will give you 0 plus 1 over n. So here you will get limit n approaches to infinity 1 and you will get 1 and that is not equals to 0. So using the divergence test 8.15, that is on page number 336, you can say like the given series diverges. An here is ln n plus 1 divided by n plus 2. I can take bn is equals to 1 over n here. Now using the limit comparison test, limit n approaches to infinity an over bn. This will give you limit n approaches to infinity n ln of n plus 1 divided by n plus 2. This will be limit n approaches to infinity ln of n plus 1. I will take n common out of denominator, cancel with this numerator. I will get here ln n plus 1, 1 plus 2 over n. Now after applying the limit, this term will goes to 0, but you will be left here with this term. And you know that ln infinity will give you the undefined answer. And this is not equals to 0. So whatever the behavior you have with this bn, the same behavior will be for an. So you will say like summation 1 to infinity bn diverges. So this implies that summation 1 to infinity an also diverges by limit comparison test. Question number 26 is summation 1 to infinity ln n over n cube. Let an is equals to ln n over n cube. Here you can take bn is equals to 1 over n cube, or it's up to you. You can take bn is equals to n over n cube. This n over n cube, that is equals to 1 over n square. The answer will be same. You can take any bn. I am taking this bn. You know that your bn, summation 1 to infinity, bn is convergent. So this is by the basic comparison test. So by basic comparison test, your given series also converges. It is convergent because of P series, and you know that P is 3 here and it is greater than 1. So it is convergent. Now consider this denominator, n square plus cos of 2n minus 6. This will be always less than n square because here you have addition of two terms. So if you just remove this one term, you remove this term, both will be the same. But if you add some term here on the left side, this will become greater than this n square. Now you have it's in 1 over this form, so just take its reciprocal. 1 over n square plus cos of 2n minus 6 will become less than now 1 over n square. Now I have here this under root n in the numerator, multiply under root n on the both side. Under root n over n square plus cos of 2n minus 6 will be less than under root n over n square. Now simplify this term. This is n raised to power 1 by 2 over n square. This will be equals to 1 over n2 minus 1 by 2. So this will be equals to under root n over n square plus cos of 2n minus 6 will be less than 1 over n raised to power 3 by 2 here. So by basic comparison test, you see that this is convergent series. Your an here is under root n over n square plus cos of 2n minus 6, and your bn here is 1 over n raised to power 3 by 2. And you know that summation 1 to infinity bn converges. So by basic comparison test, your summation 1 to infinity an also converges.